Hey everyone, this highlight video is the first of two that are going to discuss how the structures of acids and bases influence their strength. Once we know this relationship between structure and acid or base strength, we will be able to look at acids and bases and predict or rank their acid or base strength. This is going to be important as we go forward. Two basic relations we need to know before we go into this has to do with the relationship between acid strength and conjugate base strength. So if we look at this generic acid-base reaction right here, HA is our acid, A minus over here, this is the conjugate base. Okay, what role does water play in this reaction? Water is acting as a base, and hydronium ion is the conjugate acid. All right, so let's look at these two statements here. A strong acid has a stable or weak conjugate base. So that means that if this acid here is strong, then its conjugate base is going to be weak. All right? And alternatively, if this acid is weak, if HA is weak, then its conjugate base will be strong. Okay? Unstable. So there's always an inverse relationship between the strength of an acid and the strength of its conjugate base. Therefore, when we're trying to identify strong acids, what we want to do is identify stable conjugate bases. So we want to look for stable conjugate base. All right, so in these two videos, what we're going to do is talk about the structural characteristics that can lead to the stabilization of a conjugate base. All right, we have 5 different criteria that we're going to look at. The first two involve element effects. Okay, these are going to be different acids where their conjugate base, this A minus, has the minus charge on a different atom. So the minus will be on different elements, not just different atoms. All right, and so this is going to be part 1, the first video. 3 through 5 are going to be situations where the minus charge will be on the same type of element. Okay, so we might have acids that yield, 2 acids that yield conjugate bases where there's a minus charge on oxygen. All right, so we still have to be able to identify the stronger acid. Let's look at element effects. All right, so in this slide, I have a list of 4 different acids. So what's the difference between these acids? All right, if we look at these carefully, we notice that we have hydroiodic acid, hydrobromic acid, hydrochloric acid, and hydrofluoric acid. So we have different halogens in these acids. So let's go ahead, because we want to analyze or consider their conjugate bases, let's go ahead and draw out the conjugate base for each of these acids. Okay, I'm not really going to balance these, I'm just going to draw the conjugate base. So for hydroiodic acid, we have iodide is the conjugate base. For hydrobromic acid, bromide. Hydrochloric acid, chloride. Hydrofluoric acid, fluoride is the conjugate base. So the next thing we need to do is consider these conjugate bases and try to discern their differences in stability. Which one is the most stable? So what do we consider? Well, one obvious thing that we might want to consider is electronegativity. Right? So we have halogens here, we have fluoride at one end, iodide on the other end. Which one is more electronegative? Okay, fluoride. Fluorine is the most electronegative atom. Okay, so this is getting to be more electronegative. What we've learned before is that more electronegative elements can more easily hold a minus charge. So if we consider electronegativity, then this would probably lead us to thinking that we're going to a more stable conjugate base, right? Okay, so, and that would lead us to saying that HF is a stronger acid than HI, right? So stronger over here. Okay, so what's a measure of acid strength? Okay, so the measure of acid strength that we're going to use is the pKa value, right? And we know as pKa values go down, get smaller or even negative, that represents a stronger acid. Higher pKa values are for weaker acids. Okay, so here are the pKa values for these acids. Okay, so HI has a pKa of minus 10. All right, HBr minus 9. HCl is minus 7, and HF is positive 3.2. All right, so were we right? Is HF the strongest acid? No, so this whole rationale doesn't work. So what other quality or characteristic of these halogens changes as we go from iodide to fluoride, right? We looked at electronegativity, but that didn't explain our observation of acid strength. So what else changes? Another thing that changes is the actual atomic size. So we know that as we go from fluorine, here, if we go from fluorine to chlorine to bromine to iodine down the periodic table, we know we're adding layer after layer of electrons and orbitals. So it's getting bigger as we go down. Okay, so here the size, let's just write it as x minus, this is the conjugate base. The size of the conjugate base increases. All right, so how would that influence the stability of the conjugate base? Well, it turns out that if we have a minus charge and we can spread or delocalize that charge over more atoms or a larger space, then that helps stabilize the anion. All right? So we saw when we talked about resonance, resonance involves sharing or spreading out charge over multiple atoms. In this case, having a larger anion is able to spread the minus charge out over a larger volume. Okay, so we get more stable conjugate base, and so our acid strength increases as we go from right to left. So stronger acid. Okay? Here's another set of acids. Okay, we have methane, ammonia, water, and hydrofluoric acid. So just like before, let's go ahead and draw out their conjugate bases. Okay, so for something like methane on the left here, what do we do in order to draw their conjugate base? Well, we need to remove a proton. Right? So if we take off an H+, we're going to be left with CH3, and those electrons are going to stay behind. And so this is going to have a minus charge here. I'll go ahead and write in H+. So these are more like balanced this time. Okay, so we get this carbanion. If we do the same thing for ammonia, remember ammonia has a pair of electrons already on the nitrogen. We have then NH2 minus plus the proton. If we do it for water, we know if we take a proton off of water, we get hydroxide. Now, oxygen has 3 pairs of non-bonding electrons. And we do the same thing with hydrofluoric acid. We get F minus. Fluoride has a complete octet around it, plus H plus. Okay, so just like before, what we want to do is look at these conjugate bases and ask ourselves which is more stable. Okay, so we have a minus charge on carbon on the left. We have a minus charge on fluoride on the right. And so in this case, like before, an obvious difference is if we look at electronegativity. So if we go from left to right, we have increasing electronegativity. All right, so a more electronegative atom should be able to better hold the minus charge. So this would make us propose or predict that this is going to be more stable conjugate base as we go from left to right, which would then lead us to predict that our acid strength also increases in left to right from methane to HF. Okay, so we basically went through this same rationale last time, but it didn't work. All right, so what do you think? Is it going to work this time? Okay, so let's draw out the pKa's again. Okay, so the pKa of methane is clear up at 50. All right, super high. This is an incredibly weak acid. Ammonia goes to 38, so it's going down. Water, about 16. HF, 3.2. All right, so it does get more acidic as we go from left to right. And so in this case, it is the electronegativity of the atom holding that minus charge which is most important. So what's the difference between this example and the last one? Well, on the last one, when we were going up and down the periodic table, the atoms were changing in size. All right? When we go across the periodic table, these atoms, carbon, nitrogen, oxygen, fluorine, are roughly the same size. Okay? So the electronegativity effects predominate when the atoms are the same size. Okay, so the most important thing that we were looking at here was electronegativity. But here, atoms, same size. Okay, so the trends that we've been talking about are shown on this slide. Notice going from left to right across the periodic table. Remember, these are atoms that have roughly the same size. We see a lowering of pKa or an increase in acidity. Remember that the reason for this is that the conjugate bases become more stable because they have an atom that holds a minus charge that's more electronegative. As we go down the periodic table, the pKa's also get more negative. That means it's increasing acidity. And remember, in this case, this has to do with size. This is with electronegativity up here. As the atoms holding the minus charge become bigger, they spread the charge out more, and that helps stabilize the conjugate base. Take a moment and see if you can work out this problem. So like what we did before, if we want to rank acids in the order of their acidity, we need to consider their conjugate bases. So let's go ahead and draw out the conjugate bases. Remember, each one is going to lose a proton. So on the third one, as well as maybe the first one, we might have the question of which of the protons are the ones that are going to leave. So if we look at this third example, we see that there are protons on all of these carbons. And we have one proton on the nitrogen. All right, so it's the one on the nitrogen that would be the most acidic because nitrogen is more electronegative. So that gives us a conjugate base that looks like this, with a minus charge there. Actually, there'd be two pairs of non-bonding electrons, and in the last one, this would be the conjugate base here. All right, so the question is, which of these conjugate bases is going to be most stable? Okay, so there's a number of things to look at. The first thing we're going to look at is the size of the atom holding the minus charge. All right, if we look at all of these, we have two atoms that are in the third row of the periodic table. That's chloride and the sulfur anion, the sulfide. And so chloride is more to the right. It's more electronegative than sulfur. And so the most stable is going to be chloride. So this is going to be the most stable. This is stability, followed by the sulfide. And then we have the oxygen anion and the nitrogen anion to compare to one another. So the next most stable is going to be this oxygen anion. So this is a conjugate base of the alcohol because oxygen is more electronegative than nitrogen. And so this is going to be 4. So this is in order of stability. And so then the order of acidity is going to follow the same order. So hydrochloric acid is going to be the most acidic. This thiol here is going to be second. The alcohol is third. And this amine is fourth. So try this next problem on your own.